Hello, my name is Jeff Burgart, and I'm going to be speaking briefly about the State of Stress Analysis Tool, or SOSAT. So I'll start by just giving a brief overview of the tool. I don't have a lot of time, but for those of you who aren't familiar with it, I'll just provide a little bit of background. Then I'm going to talk about the feedback we've received from beta testing over the last year or so, and finally, the plans for this fiscal year. So the State of Stress Analysis Tool is really about quantifying geomechanical risk. And I define geomechanical risk in two ways. One is focused on leakage caused by unintentional hydraulic fracturing. And this occurs when pore fluid pressure exceeds the minimum principal stress. And this can occur in either the reservoir or the cap rock or adjacent formations. And the other is induced seismicity, which is a little bit, well, a lot harder to predict, but stress, we believe, plays a role in it. And so this is caused by changes in stress on a fault induced by elevated pore pressure, or can be caused remotely, indirectly, by changes in stress, even where the local pore pressure is not elevated. So I want to just talk very quickly about the current regulatory requirements and how SOSAT would fit into those. So focusing on the EPA Class 6 language, I just have a highlight here of one of the requirements specifying that the injection pressure must not exceed 90% of the fracture pressure or minimum principal stress. And in no case may the injection pressure initiate fractures. So in order to meet this requirement and specify at a site what your maximum allowable pressure is, you need to know what your fracture pressure is. And so to do that, we need to know what the fracture pressure is both in the reservoir and the cap rock. And a conservative way to do that is to assume the fracture pressure is equal to the minimum principal stress. So a later section of that document talks about how an operator should go about meeting this requirement, and it refers to a set of papers and test methods to measure stress. And all of these are, for the most part, hydraulic fracture based, and SOSAT is consistent with these recommendations and is applying methods basically very similar to those in the papers, just the methods in these papers are deterministic in nature, whereas SOSAT maps uncertainty through these workflows. So where current techniques are deterministic, such as saying the injection pressure can only be 90% of the fracture pressure, implicit in that statement is fracture pressure is a deterministic and known value, which is almost never the case because stress measurements, where they do exist, are often unambiguous or at least have some uncertainty in them that needs to be accounted for. So SOSAT implements a rigorous Bayesian uncertainty quantification using these standard stress estimation methods. And the output of this analysis is a joint probability distribution for the principal stresses. And then you can derive from that things like the probability of shear or tensile failure given the available state of information. So just some examples of this. So just working through top to bottom is less data to more data at the bottom. The center column is the joint probability distribution for the maximum on the vertical axis and minimum principal stress, horizontal axis. And where darker colors mean higher probability density. And so the left column lists what data is the input. So basically, as more and more data is available and input into the model, the stress state becomes more and more constrained. And the plots on the right show the probability of activating a critically oriented fault at a given pore pressure. So as more data is available, those risks go down as we know more about the site. So the feedback from beta testing that we've received over the last year or so, several users thought that the tool was too conservative, i.e. overestimated risk. And that is true, but it's largely reflective to the paucity of data in these cases. So if you apply an uncertainty quantification, with a lack of data, we have to assume that, a broad range of scenarios are possible, and those will include unfavorable scenarios. Another case we found is that many of the sites that we applied the tool to had no stress measurement data. And this is, again, similar to this first point, in the absence of this data, you're really not going to meet the regulatory requirements, and the tool is going to lead to, showing non-zero probability of unfavorable conditions. And the other thing is users often want to be able to estimate stress on a particular mapped fault, which the current version of the tool doesn't have, but is a feature that we will add this year. So speaking of which, plans for 2021, we're going to actually add a web-based GUI with embedded documentation. I think that'll be much more flexible and user-friendly than the current GUI. We're going to switch to a different sampling strategy that will perform better under a broader range of constraints that I've listed here. Finally, we're going to add a formal documented testing suite. What we've had so far has just been kind of ad hoc, and we're planning to release it under an open source license, so it will be more broadly available and available to modify by a broader community. And that's all I have time for today. Thank you very much for your attention, and please reach out to me. I'd love to talk more about this if you have any questions.
Greetings, this is Ernest Lindner, and we're going to talk a little bit about NRAP seal modeling efforts over the last few months. Now, when we talk about the seal ROM, we're talking about a representation of the cap rock over the storage reservoir. We've made several updates to the seal ROM since April. We've added new error checking and debugging options to make it more user-friendly. We have free-form cells added to the code for defining cell locations, in contrast to the format that we had earlier. We have most significantly added a new capability to estimate equivalent permeability into the fracture networks. And we'll talk a little bit more about this in the next slide. We are also in the process of incorporating the seal model into the NRAP IAM, and we're also looking at the option to incorporate a reservoir model directly into the standalone code to make it more user-friendly. In summary, the code, the seal ROM, as we call it, seal flux, has now a stochastic fracture generation capability. Seal flux can now generate or create a set of random fractures for each grid cell across the study area and then assess the permeability of that network. Fracture generation uses geologic knowledge, fracture density, strike, length, aperture, together with stochastic functions to generate this network. Also in the model, we can use or include user-defined fractures and matrix permeability so that in the event that we see a feature we need to add into the network or define throughout the study area, we can add that. We can also include a matrix permeability, which, when there are no fractures or very few fractures, will be added with the fracture permeability to compute a total permeability for the area. Now, these new additions include also a entry pressure aperture and an aperture length correlations to help us tie together the network generation and to make sure it is indeed realistic, like where a large fracture would have less of an entry pressure than a tighter fracture, which would have a higher entry pressure. Now, the new version is written in Python 3.7. It's using a IDE under Mac OS. We've used both Spider and PyCharm. The current version of the seal ROM is now beta 2.0, and it's available on the GitLab site. It's also on the EDX. If anybody has wished to download the code, you can readily do so. Now, work on the seal frax code, which we generated earlier this year, has been halted as the seal frax capabilities are all included in the new seal ROM. If anyone has any other suggestions for a seal ROM or any additions or new options or criticisms. We'd like to hear from you, and please just send me an email and I'll get back to you. Well, that's it. Thank you for listening. This is Ernest Lindner again, and we're briefly going to review NRAP fault modeling efforts in the last few months. When we talk about faults, we're talking about leakage along a structure from the reservoir to the groundwater aquifer. We're not talking about seismicity, as that's addressed by other ROMs and codes. So NRAP has developed a new IM fault ROM to address potential leakage. The new ROM, called Fault Flow, includes two-phase flow and a Brooks-Corey model for relative permeability. Density and viscosity can be interpolated by the code from temperature and pressure at the reservoir horizon. It incorporates fault variability in strike and aperture between simulations. It includes an SGR factor for normal faulting considerations and a state variable for corrections of near surface flows. Now, near surface in this regard is where the supercritical fluid transitions to a fluid and then to gas near the surface of the Earth. Some notes on the code is that it's segmented for more accurate representation, so it's not a single line element, it's a multi-line element. Fault orientation is projected from the surface to the depth to help the user position the feature. It's developed under an expedited schedule to permit concept reviews. In other words, to permit user input on how this fault ROM addresses the concerns that they have. Is there something missing? Is there something that could be added that would help a lot? Or is there too much in the code? Any input on that would be appreciated. It also is going to consider in situ stress and near surface flows in a more explicit fashion in the next version. The code is currently written in Python 3.7. It is a standalone beta at 1.2, which is available on GitLab and on the EDX. We understand that an alternative fault model will be available shortly as developed by Lanel. I don't have any additional details on that. But in any case, we have a new fault ROM, and I would appreciate any criticisms that users might have on the code. Thank you.